All right, so when an object is moving at a constant velocity, the acceleration is 0. Just like in any of the other cases where acceleration was 0, it's still in equilibrium. It's still in equilibrium. So that means that when I sum the forces in the x direction, the forward force, the applied force that you pulled on the block with, minus, because this kinetic friction force is to the left, will have to equal 0. So these two vectors are the same size. Those two vectors are the same size. It's not accelerating. Now for the moment when you grabbed the spring scale and you were pulling it to the right and it wasn't moving, and then there was a moment where it slipped and started moving, that situation was unbalanced, disequilibrium, non-equilibrium, and it accelerated. But once you got it going and then you adjusted the spring scale so that the force was measuring about the same number the whole time you were pulling it, the forward force and the back force, the friction force, were equal to each other. Okay? It's when you increase that forward force that it would accelerate and they would be unbalanced. Or when you decrease that forward force and the friction force stays the same and it decreases and decreases and the object slows down. That's what happens when you slow down in a car. You disengage the engine and you start the brakes and you're causing friction and no forward force and you slow the object down. It's an unbalanced situation. So when we're moving at a constant velocity, we're still in equilibrium. So that means that the sum of the forces in the y direction, and you guys told me that the up force, the force from the table, the one we called the normal force, was balancing the gravitational force, and the normal force is positive, so there's an understood positive right there. The gravitational force is pointing down, so that negative takes care of that direction. You sum them up and you get 0. So if I look at these two equations for the forces, if I go here, let me grab this, I'm just going to write this down here, I like arrows. So wouldn't the applied force be equal to the force of kinetic friction? If I rearrange this equation right there. And what about this guy right here? If I were to rearrange him, wouldn't the normal force equal the weight or the gravitational force? So yesterday on your graph, you came up with an equation that was like the force applied was equal to a slope times mass. Is that right? So now, look, I can make a substitution. Boom. If the force applied is the kinetic friction force, then I can make an equivalent substitution there. Times our slope value. All right. Now, mass, m. Is there anything wrong with multiplying by g and dividing by g right there? Now, F of force of gravity, F of g, we determined that equation a couple of days ago. What's the gravitational force equation? Do you remember? F of g equals mg, exactly. So now, look, that means if mg equals F of g, which F of g equals the normal force, can I stick this guy in right there? I'm just making substitutions into the equation that you created. So now I get the force of kinetic friction is equal to whatever your slope value was divided by g times the normal force. Now this value right here is constant for the surface to surface interaction. This right here is the coefficient of kinetic friction. And we use that symbol mu. So mu k. So your force of kinetic friction is equal